Then he was a postdoc, spent several years at ASU, and since 2001, he's been on the faculty here. Since 2011, he's been leading the OSIRIS-REx mission. And in the last few days and weeks, we've come to know some interesting new things. So when this mission was launched, I remember there was some LPL event, and I asked Dante, so why do we need to spend $1 billion going to an asteroid to get a tiny bit of a sample when we get this free thing from nature, meteorites falling on the Earth constantly? And that doesn't cost very much. Well, maybe it costs some, but it costs some, right, to go grab a meteorite that falls freshly. But yeah, $1 billion. So Dante and I think Tom Zaga was there, and they both jumped at me, and he said, it's the context, okay? So we're going to know the context right now, right? Okay, thank you.
Right. All right. As I like to say it, meteorite scientists are geologists that have been poking around in the stream bed for a couple hundred years. And now, for the first time, we're walking up to our outcrop. So if we have any field geologists, I hope you can appreciate that. We're really seeing the landscape where these rocks come from, and it's already fascinating. It's early days on OSIRIS-REx, but what we've learned so far is really fascinating. It's been a long journey. Renu mentioned the 2011. That was actually a pretty tough year. That's when the first PI, Mike Drake, passed away, and I stepped up into the leadership role, probably one of the hardest things I ever had to do. And not what I signed up for when I got involved in the mission, but it's been a great ride ever since then. I would say up until this past month, my favorite part of the whole experience was the launch campaign. So we got to move to the whole family, wife and 2 kids, picked up, moved to Cocoa Beach for 3 months, got a nice beachfront condo, and I got to go to work every day at the Kennedy Space Center and watch the final stages of the OSIRIS-REx spacecraft, going through its checkout and fueling, and ultimately encapsulation. This is the fairing of the Atlas V that we launched in. So I always start out with this slide. I'm really proud of the fact that I got to be there and see the spacecraft come to life. And it's kind of a transcendental experience to launch something like this into outer space. And you become jaded because now every day I wake up and I get my coffee and I log into our data server and I look at the latest images that are coming down from the asteroid. And you kind of forget the work that went into it and the extreme amount of talent that's gone to making all of that happen and all of that data to come back to Earth. So the mission name is an acronym that describes the scientific objectives of our program. We are going after origin science. We're trying to peer back to the dawn of the solar system to see where these hydrated and carbon-rich rocks come from that do rain down on the surface of the Earth. And as we try to pick apart their very detailed molecular chemistry, contamination issues crop up and context issues crop up. You don't know where they're coming from, and you have a hard time putting it into the broader picture of the current structure of the solar system. We do spend a lot of time trying to understand the composition of the asteroids and small bodies and all solid bodies in the solar system with spectroscopy. And we particularly chose a very dark, low albedo asteroid, and trying to get spectral information from those kinds of targets are very challenging. And as we're seeing, there's a lot of data in the spectral properties of the asteroid that you simply can't infer from the ground. So we want to have that ground truth and make that connection. And not just spectroscopy, but really all the ground-based astronomical techniques. And that's kind of how I organize my presentation today. It's been for years now, 7 years or more, I've been giving talks about everything we think we know about the asteroid from ground-based and space-based telescopic characterization. And so now you guys can kind of grade us. How did we do in assessing the properties of the asteroid? I also wrote down resource identification as kind of a far-out sci-fi fantasy of mine that we'd be mining asteroids. But from what we've learned already, Bennu is pay dirt for an asteroid miner, so we're very excited about that. The security aspect deals with the Yarkovsky effect, and I'll talk quite a bit about that in the presentation. And then we are, hopefully, and it's something we'll talk about as well, a regolith explorer. We're interested in bringing back a sample of the regolith. The challenge, as you'll see, is going to be to identify it. So these are just some of the assets that we're able to get time on in order to characterize our target asteroid. And it was a phenomenal astronomical campaign. And as a result, Bennu is the most well-characterized body in the solar system from an astronomical telescopic point of view. And definitely the most well-characterized asteroid that had not, as of this time or this era, been visited by a spacecraft. So we were able to use Arecibo and Goldstone planetary radio systems to get the radar properties, and those were incredibly valuable, and we've validated a lot of that data. But we also did a lot of photometry and astrometry and spectroscopy, looked at scattering properties, and now analyzing the spacecraft data and ultimately the return sample will really help us validate and provide ground truth for this approach. So I love this slide. I've been showing it. This one has been kind of my standard go-to Bennu slide for years. Summarizes some of the most important things that we needed to know about the asteroid and why we chose it for our target. So over here on the left is the orbit diagram. The Earth's orbit is in green, and Mars is the outer white circle. And here is the orbit of our target asteroid Bennu. It is a near-Earth Apollo-type asteroid, and it crosses the orbit of the Earth right around here in the fall. If you look at it more obliquely, you can see it has an inclination of 6 degrees, still crosses the Earth's orbit even in this field of view here. And of course, that was really important for target selection because we needed an object that we could get to, rendezvous with, and then come back with a sample. And something that's in a relatively Earth-like orbit and a very low inclination greatly facilitates that process. And then over here are the radar data. These are some of the best data from Arecibo. And Mike Nolan, who's now a research professor here at LPL, was running Arecibo at the time and processed the data to produce this three-dimensional shape model here. And it's a pretty grueling process if you haven't been through this. It's forward modeling, so they start out with a triaxial ellipsoid because you can get the basic size of the body from the data, and then they work at the radar resolution, which is really your timing resolution, how quickly can you discriminate return signals from one another, gives you a resolution of 7.5 meters, and facet by facet, they tweak it until it predicts the radar data. So what Mike came up with and the team was an average diameter of, mean diameter of 492 meters. This spheroidal spinning top shape with a pronounced equatorial ridge, retrograde rotator with a period of 4.3 hours. And I'll talk about this number quite a bit, but we actually constrained the bulk density from our ground-based astronomical techniques to 1260 kilograms per cubic meter. We knew it was a very dark asteroid. We constrained its albedo to 4.5%, plus or minus 0.5. And it's a B-type asteroid, which we had done a lot of work to link to carbonaceous chondrites, a type of meteorite, a specific subset of the carbonaceous chondrites that are volatile rich, have water in them, and are rich in organics. And that's really what we were hoping to find when we got to the asteroid. Here's an overview of the operations timeline. So that launch was in September of 2016. We did an Earth gravity assist almost exactly 1 year later, and we used the Earth's gravity to slingshot us up onto the trajectory of Bennu, to rendezvous with Bennu, so that 6-degree inclination plane change. And then in October, we did our first asteroid approach maneuver, starting the approach campaign, and asteroid operations kicked off with the preliminary survey phase in December. And we have a long time at the asteroid, so that's really good news because we've got quite a challenge ahead of us to get a sample off of this body. So we're looking at all of 2019 as detailed mapping and site selection and then rehearsals, and the nominal baseline plan is to collect the sample in July of 2020. Our departure window opens up in March of 2021, so we have some time here if we need it. The good news is there are trajectories that leave Bennu as late as April of 2022, still returning the sample on September 24th, 2023. We have a very capable spacecraft, and I'm incredibly proud of the team that built the spacecraft and built the scientific payload and perform all the spacecraft operations and science operations. And the science operations are all centralized here in Tucson at the Michael Drake Building, which is just off campus. So we here at the University of Arizona, we built the OSIRIS-REx camera suite. That's a suite of 3 imagers, the high resolution, very narrow field of view PolyCam. It's the PolyCam because it's got a focus mechanism for its secondary mirror. So right now we're set at an infinity focus, but we can actually translate that and we can focus at ranges as close as about 200 meters from the surface to get really high resolution shots. And then we have the MapCam. You'll be seeing a lot of data from both of these imagers today. The MapCam is our color imager. It's got a filter wheel with 4 color filters that correspond to the B, V, W, and X astronomical filter set, which are commonly used for characterizing asteroid colors and classifying them. And you'll see one photo from the SAMCAM. That's there to watch the TAGSAM, which is our sample acquisition mechanism, and to document the interaction with the asteroid surface. We have a phenomenal set of spectrometers. It surprised me when I realized that OSIRIS-REx is the first mission to fly both a visible near-infrared spectrometer and a thermal emission spectrometer. So we have coverage with OVIRS from 0.4 to 4.3 microns, and then OTES from 5.5 out to 100 microns. So we have phenomenal spectral characterization of the asteroid, and that is really paying off. We have another spectrometer, the Regolith X-ray imaging spectrometer. That is a student experiment that was built by a team of students at MIT and Harvard. And we don't have any data from them from the asteroid yet, and they're still working through their calibrations and checkouts of their instrument. But they've learned a phenomenal amount. It's been a great program. Students literally designed, built, tested, and are now operating and processing the data. And from our Canadian partners at the Canadian Space Agency, we have the OSIRIS-REx laser altimeter. We just got the first data over the past couple of weeks. They're still pushing that through and checking their software, so we won't be showing OLA data yet. It was really just an early look for them. Here's just a little more detail of what we've been through since the approach phase began. First light of the Bennu was in August of 2018. And then we really started doing some phenomenal imaging right here in mid to late November, and then early December, right before the preliminary survey came up. This was just a series of maneuvers to slow us down by over 400 meters per second relative to the asteroid, setting up polar and equatorial passes of the asteroid to probe the asteroid mass and get some variable looks at the northern and southern polar regions of the asteroid. And we're planning an orbital insertion for New Year's Eve of this year, and everything's nominal for us to proceed with that timeline. So December 31st, we'll go into orbit, and that's the final stage of the navigation campaign. So the good news is as phenomenal as all the data that we have right now are, it really is just to kind of get our bearings, and the real science campaign starts at the end of February next year with the site selection campaign, where we have 2 different kinds of detailed surveys. Ones we call the baseball diamond, one we call the equatorial stations, really vernacular for referring to the emission angles and incidence angles and phase angles that we want to look at the asteroid. And then we get back into orbit for the science orbit campaign, and by September of next year, we will have picked a couple spots on the surface as potential sample sites and be doing those low altitude passes at a couple hundred meters to verify their safety and sampleability. And if everything looks good, we start rehearsing sample acquisition with a goal towards the touch and go maneuver in July of 2020. So some of the first things that we did in the approach phase were to scan the asteroid environment. When we did the ground-based telescopic work, we had no indication of satellites. The light curve looked pretty consistent with a spherical object with no secondaries around it. The radar didn't pick up anything. So there was no indication that there was any satellites, but we had to make sure. And so a lot of our early work was scanning the environment, not only for satellites, but for dust plumes, and we looked for dust along the orbital path or along the solar vector. And Bennu looked really hospitable. There was no reason to be concerned, and we did really well. You can see here, this is the distance from the center of the asteroid, so this inner circle's 300 meters, 500 meters, and out to a kilometer. And we were able to detect within, so this is, remember, about 500 meters, within about 50 meters of some points on the surface, objects as small as 8 centimeters. So we really were confident in clearing the operational environment from any hazards. And then I just want to remind you of what we predicted the shape to be. This was the Earth-based radar. This was the pre-arrival predicted shape. And then here is the comparable images. So as this rotates around, notice that we did have indication of a boulder on the surface of the asteroid. We estimated that object to be about 10 meters, and that was the only real distinctive boulder that we saw on the surface, and I'll talk quite a bit about that as we go forward. That is right there. Colloquially, we were referring to that as Ben, which is from the Egyptian mythos. That's the rock that Bennu stands on. So Mike Nolan named it that many, many years ago, and it's certainly stuck. But overall, he did really well. I mean, this is a great validation of the radar technique. This is the first time we've had this kind of resolution of a radar shape model that we've then been able to go and compare to images. The size is just about right. It's a little squatter than we thought, but the largest uncertainty was in the polar axis. We had put 50-meter uncertainty on that at the 1 sigma level, and he came within that range. And even some of the features that we weren't sure, like some of these kind of more valleys or these northern ridges, appeared real in the shape. So this is a great validation of the radar technique for shape modeling. And this was really good news because we kind of designed the whole mission around this shape being accurate. All of our trajectories and all of our look angles and everything were really based on that. So that was outstanding. Some other details of the shape. One of the interesting things is when we start to look at the polar views, here's looking down at the positive pole, and here's looking at the negative pole. We thought it was going to be a lot more circular, and in fact, a few of these other asteroids, even asteroid Yugu, which the Hayabusa 2 spacecraft are at, they have a really nice circular definition to their equatorial ridge. Bennu does not have that. It's got a lot of depressions and ruggedness, and it deviates substantially from a circular circumference. And it really lacks a distinctive bulge. It's much more rounded than we kind of expected. We thought this would be a nice sharp peak, but it's just an oblate spheroid. I'll talk more about this second point, but there are topographic high-standing ridges in the northern hemisphere, and we do see evidence of downslope movement that are being controlled by those ridges. They're kind of forming valleys. The south doesn't show any of that. It looks smoother, although there's large concentrations of boulders in the south. And we're still working on this. This has been confounding the team as they try to process the shape model. This is all done with a technique called stereophotoclinometry, where you process using both stereo techniques as well as shadowing to come up with the shape and the rotation state of the asteroid. And we are not getting a pole to converge as of yet. So we're thinking that the object might be wobbling, which would be pretty exciting to the dynamicists that are out there to try to understand when that might have been induced and what the damping time would that be. We still need to confirm it. Not everybody thinks it's there. Some people think it's just errors in our pointing knowledge or in our kernels. So that's still going on, but the altimetry group they're not giving up on that right now. They're still holding that as an explanation for the failure to converge on a pole solution right now, which is the team is experienced. They've done this for many small bodies. They did it for Ryugu, they did it for 67P, they did it for Itokawa. All of those converged to a pole very quickly. We have a phenomenal data set, and so something's up, either in the data system or in the imaging conditions or in the asteroid. And then, of course, this has been the most phenomenal data product. You can imagine that we have sat and stared at this for a long time already. These are the best data that we acquired right at the end of the approach phase. So on December 2nd, right before we arrived at Bennu, we took these series of PolyCam images. These are each 12 images that have been mosaicked together, and then you see the rotation movie put together here with a resolution of 33 centimeters per pixel. So one thing I'd like to point out is that that scale is coincidentally almost exactly the diameter of the sample head that's going to collect the sample. So we are going to sample 1 pixel on this mosaic right now. So the challenge is going to be which one do we pick and where do we go? And this is at a relatively high phase angle of 48 degrees, so it's showing a lot of topography. But a couple things that jump out, and I'll talk about this more, but there's certainly this object here, the large boulder that we spotted, is about 50 meters across. We estimated it to be 10 meters, and we also said that that was the only 10-meter sized boulder on the surface. We're up over 700 10-meter sized boulders or larger that have been counted on the surface, and the team is still going, although I think we're converging on the total amounts here. So the surface is a lot more rugged than we expected. It also looks older. There are impact craters, especially as you watch over here as it rotates into the terminator. It looks like there's some big circular basins, crater candidates. We're being careful right now not to definitively say that these are impact craters or not, but they seem to dominate, and there seems to be concentrations of them along the equator. Also, just paying attention to this view over here, you can see how rounded it is here. It really doesn't have this sharp peak ridge, which Ryugu does. The Japanese target has a very much more pronounced equatorial ridge. And I'll get into some of the details of the geology here, but you can see wide variations in the reflectance properties. In fact, I think if we go to the next one, this is at a much lower phase angle, 5-degree phase angle. Not as great a spatial resolution because we were farther out back in late November here. But the color variations that you see here are true reflectance variations, and this just kind of shows you the last mosaic was at 48 degrees, so kind of like the frame up here on the top. And then as you go to smaller and smaller angles and you get to these very low phase angles, you're really bringing out the albedo variations. So you can see one of the things that got us excited right away are that there are definite very dark spots on the surface, including this very large dark outcrop right here. This seems to be somehow getting revealed. It looks like it's a topographic high, kind of a mound, but it looks like it might be weathering all around it. And then throughout the surface, there are some really bright objects. In fact, this one here really stood out to us, and it persists. You know, at first we thought that it might have been just because it had a specific phase angle or face to us, but watch it as it rotates across the surface. It is bright at all different look angles here. This is a really highly reflective material compared to the baseline of the asteroid. So a lot of reflectance variations on the surface, a wide diversity of material types, which makes it very exciting, and also it's going to make it very challenging as we move into the sample site selection phase. Here's just zooming in on one of those high albedo features. So the good news is we estimated 4.5% geometric albedo. Global average is coming in at 4.4%. Not too surprising since we had such a great shape model of the asteroid. We knew its area that was exposed, so we're pretty well validated that technique, but we didn't expect that. Darkest materials, those dark spots like these guys here, getting down to about 3.7%. The brightest materials, 10 to 15%. We're even getting some of those really bright spots up to 17%. And that's actually not that bright as planetary surfaces go. It's kind of like CV chondrite or something like that, as opposed to these really dark albedos, which would be more like the carbonaceous chondrites that we are interested in here. Okay, let's step back and think about the spectral properties a little bit. So these are going back to some data that we published in 2011. This is the data that Beth Clark compiled. It was data collected in 1999 by Ellen Howell and as well as by Rick Binzel in 2005. And it's a B-type asteroid, and that really is characteristic of this continued increase in reflectance as you go to shorter and shorter wavelengths. There's no indication of a drop-off in the UV, which we see in most asteroids. Carl Hergenrother used the ECAS filter set and pushed it down even to shorter wavelengths, down to about 0.3 microns, and we see that in the filter photometry, you still are getting increases in the reflectance of the asteroid. So there's no sign of a drop-off, and it clearly belongs in the B type of asteroids. And then we tried to match it to different types of carbonaceous chondrites. And the one that kills us, that's always been kind of, I would say almost a bane, is that the best fit, these are from the Relab spectral database. This is a CI chondrite, Ivuna. We would love to be at the parent body of a CI chondrite. They're very rare. There's only 5 of them known on Earth. Most of it, 90% of it, is a single fall that landed in France in the late 1800s, very contaminated and poorly treated over that time period. But in order to get the spectra without the UV drop-off, they had to heat it up to 700 degrees. So we were always worried that we were looking at a really thermally processed asteroid, probably dehydrated. A lot of the organics would be either volatilized or polymerized into kind of a tar. We did see maybe matches to the CM chondrites, much more abundant, still pretty rare, but on the order of 150 kilograms total on Earth. But again, they have the UV drop-off, which we're not seeing with Bennu here. But we decided, after looking through both the albedo space and all the spectral slopes, that indeed it's most likely that Bennu is similar to a CI or CM chondrite, and we settled in on a CM1-like material. This was comparable to asteroid Themis in terms of its albedo and near-infrared spectrum, and Themis is a well-known B-type asteroid that was, became pretty prominent when a series of papers were written a while ago detecting water ice and organics directly on its surface. So we were excited to be compared to Themis. It also looks like Pallas, which is one of the largest main belt asteroids, also a B-type. More similar to that as you go out to the longer wavelengths, 1.6 to 2.3 microns. So our guess was that we're looking at hydrated, carbonaceous chondrite-like material, possibly thermally altered, and would have lost all of its hydration features. We have done some color mapping, not great resolution. We're about 11 meters per pixel here with all 3 MapCam filters. Here we're looking at the composite in the BV and W filters, or red, green, and blue. This is that very prominent dark spot on the surface here, and then the other data that we're showing are just the entire disk average. So over here you can see the global average with uncertainties looks pretty flat, like we would expect. Reflectances coming in just under 4.5%, pretty consistent with what we're looking for. We do see a difference when we look at the dark material only, and we're able to average about 6 pixels inside this dark spot here. And we do see a clear absorption at 550 nanometers. That's unusual. We don't see that in meteorites. We're not sure what might be causing that. We haven't got the resolved data from OVIRS yet to confirm it with the VIS near IR spectrometer, so we're just stuck with the filter photometry for right now. But we've reproduced it with some of the color data that we collected just a week ago on one of the equatorial paths for preliminary survey. So it doesn't, and I should say what we were looking for and we expected if this was going to be hydrated material is that there would in fact be an absorption at 700 nanometers, or what we call the 0.7 micron feature, which we do see on a lot of meteorites and on a lot of dark asteroids, and is consistent with oxidized iron, or iron 3+ in phyllosilicates, or the clay minerals. So the dark material isn't showing us any sign of the hydration features. But the good news is we did get OVIRS full disk spectra in mid-November. It filled only about 40% of the field of view. So OVIRS is a point spectrometer, and then it has a series of wedged filters across its detector to break the wavelengths apart. So you only get a single pixel, but you get really nice spectral resolution across that. So you can see the field of view of OVIRS is the dark circle, and then here's Bennu filling about 40% of that. So it was still pretty low signal to noise compared to what we'll get. Once we get into that detailed survey and we're doing the equatorial stations, an OVIRS spot will be about 20 meters, and we're going to get the entire asteroid at 7 different locations at local solar times around the day and get some really nice spectral maps. But this was a very good day. I remember Vicki Hamilton and Amy Simon, who are the 2 scientists leading the spectral analysis working group, called me up and wanted to come and talk to me, and they showed me the data from OVIRS, and we saw this really nice feature at 2.7 microns, and then a long, slow return to the continuum here at around 3.2 microns. Very much like what we see in our CM and CI chondrites. In fact, the CM1 seems to be a really decent fit to it here. The CI has this little upturn here. We're not seeing that right now. And then over here are the 3.4 micron organic features. Don't have enough signal to noise to tell if they're there yet or not, so that's still to be determined. But this was one of the big announcements from the press conference at the AGU, was that in fact it does look like we hit pay dirt. We do have, at least on the global scale of Bennu, a deep hydration feature. Not seen on the Hayabusa 2 target Yugu. They have maybe a very small feature here. In fact, they look like more like the dehydrated, heated type of material than we do out at these wavelength ranges. So that was pretty exciting. And then a couple weeks later, the OTES data came in, and we were able to get an emission spectra. So if you're not familiar with the thermal emission spectrometer, you get a really dominant flux from the black body emission. So you get a peak 10 to 15 microns depending on the temperature that you're looking at. And then you have to subtract out the black body, and what's left is due to variations in emissivity, and there's indications of the mineralogy in the signal there. So again, just like OVIRS, OTES is a point spectrometer. It's got 8 milliradian field of view, so it's got a bigger spot size. So when it was doing the observations back here, Bennu was filling 10% of the field of view, and the signal and noise was very poor. But then we got into the final stages of the approach phase, and we were able to get a spot on the asteroid about 200 meters in size, nice and centered right there, relatively constant temperature, which makes that temperature emissivity separation easier to do. And we were able to get some really great data, and then we were able to register it to PolyCam images that were taken on the approach to get a sense of some of the features that we were looking at. Excuse me. So on the diagrams over on the right here, the Bennu spectrum is both the black and the gray. Two different views of it. So we're seeing a lot of noise here down at the lower wavelengths. But you see that we have this nice, in fact, let me pull this in. Let's focus in over here at 23 microns. This is a pretty characteristic region. So if we looked at something like the most common type of meteorite on Earth, the ordinary chondrites, you would see that they have a lot of structure out here and no absorption centered there. Something that would be more anhydrous would be like an Allende or Vigorano CV chondrite. We don't see a nice match there. You start to, when you get into the type 2s like the CR chondrites, you start to see a nice dip there. But really, we're getting a pretty nice match between Murchison and Orgay in terms of the position of that band. So that's pretty exciting. Confirms the OVIRS detection at 2.7 microns that we are really looking at some material that's analogous to our CI and CM chondrites. And then the other thing to look at is the location where this drop-off starts to occur here, just past 9 microns. And again, you can see when you're looking at these anhydrous, kind of olivine and pyroxene dominated meteorites that this would be pushed way over to shorter wavelengths. And that as you get into more of these phyllosilicates, in fact, the best match is, in fact, the CM1 Allen Hills 83100 meteorite. So we're somewhere in this phase space. You know, we're getting a nice peak position match to Murchison over here at 23 microns. The drop-off at 9 microns is a nice match to the CM1 type of chondrite. This is what we predicted from the ground. So another really great illustration of the power of flying these two different spectrometers. And again, it's early days for these teams. They're still trying to process the data from preliminary survey where they've got some better spatial resolution across the asteroid surface, but they're not ready to release those yet. And then again, this is all just kind of the preliminary show with the detailed survey coming up next year to really push all of that to a much, much higher fidelity. I want to step back a little bit now and talk about some of the amazing work we did on the astronomy side and the fact that the mission can be used to confirm these kinds of results. So I mentioned the Arecibo Effect right at the beginning of the presentation. If you're not familiar with this, it's turned out to have a substantial role in the orbital dynamical evolution of small bodies in the solar system, particularly effective at changing the orbits of objects that are sub-kilometer in size, like Bennu. And it's a pretty basic idea. So you have, like Bennu, a retrograde rotator. So its orbit is moving in this direction. It's rotating in this direction opposite its orbital motion. And so its afternoon is ahead of it as it's moving through space. So being a dark asteroid with a 4.5% albedo, it absorbs over 95% of the solar radiation on its surface at the subsolar point. And then as it rotates into the afternoon and cools off, it releases that energy back out into space as a thermal emission. And that, in fact, imparts a thrust on the asteroid, and because it's thrusting opposite its direction of orbital motion, it slows it down, and its semi-major axis decreases. If it was a prograde rotator, the afternoon would be behind it, and the Arecibo acceleration would lead to an increase in its orbital velocity, and its orbital radius would increase. So we were able to measure this from the ground. We discovered the asteroid in 1999. It was discovered by the Linear Survey in New Mexico. And at the time, they were able to get Arecibo ranging data as well as resolved imaging data. It's on a synodic period with the Earth of 6 years. So it came by again, did a close approach in 2005. And we got the great radar imaging data that I've discussed already. And then it came back in 2011. It was too far away to image, but we were still able to range. So when we got the first data in 1999, we got an estimate of the semi-major axis of its orbit. When we did the data measurements in 2005, we detected a change in the semi-major axis. And then in 2011, with the third radar ranging opportunity, we got a rate of change in the semi-major axis, and that was the Yarkovsky force. And then we also had detailed Spitzer Space Telescope observations of its thermal emission back in the Spitzer cold period in 2007. And that is the acceleration term. So we had the force and we had the acceleration. We were able to apply Newton's law to calculate the mass of the asteroid. We saw it move mostly a long track by 160 kilometer over those 12 years. And then when we combine that Yarkovsky force detection with its thermal inertia and the shape model, we constrain the bulk density to 1260 plus or minus 60 kilograms per cubic meter. And that's a first of its kind measurement. I think that we should appreciate that. That's the first time the mass of a planetary object has been determined without using a gravitational perturbation. So having the mass either perturb another planetary body or a spacecraft is how we've always measured the mass of an object. Here, we attempted to measure the mass of an asteroid using the detection of the Yarkovsky acceleration and the thermal emission. And then we did do the first 3 flybys over the North Pole. We were able to get an estimate of Bennu's gravitational parameter, giving us a GM of 4.9 and a bulk density of 1190 plus or minus 24 kilograms per cubic meter. So 1260 plus or minus 60. 1190 plus or minus 24. Pretty much within 1 sigma, maybe a little bit outside of 1 sigma, we were able to measure the mass and the density of the asteroid using that technique. So we had 2 more flybys that we're still processing the data from, but the mass is really converged at this 4.9 value. So it's a little underdense compared to what we estimated. That means that the orbital parameters will change ever so slightly. But we got the Yarkovsky estimate validated to within 1 sigma and verifies this pioneering technique to estimate asteroid densities remotely. So to me, that's pretty exciting. It's not an easy thing to do. You got to have this really precise astrometry over a long time span. Over a decade is preferred. You got to have a thermal model or space-based observations. And then you got to really know the shape and the spin state using radar preferably, although you can kind of back out some of this information using photometry that's not nearly as accurate. So that's pretty exciting. We were able then, during the planning stages, we're able to say some things about the predictions of the geology of the asteroid. So we're able to measure, combining that density with the shape model and the rotation state gives you slope maps of the asteroid. So we kind of expected to see the highlands up in the polar regions and kind of geopotential lows concentrated around the equators. Tilts are distinct in that they don't have the gravitational acceleration. It's just the angle of the facet of the shape model relative to the normal through the center of the body. And we used all of that to plan the mission and even think about where we might be getting the sample from. So here's 2 different slope maps now that we have the mass and we have the shape. The first shape model came out at the facet scale of 6.3 meters, and then more recently down to 0.8 meters. This is about the requirement needed for our landmark tracking navigation. So you can see that we were broadly consistent. We do have some high slope regions here. The bright yellows are getting up to 35 degrees, and low slopes are concentrated around the equator, although it's fairly rugged leading right up to that. But overall, we do expect to see the slopes trending. Here's the positive pole. Everything would be migrating downward from the pole towards the equator. And that's not necessarily the case, right? That's really very much dependent on the rotation state and the mass of the asteroid. Ryugu, the Hayabusa 2 target, is exactly the opposite. It's spinning much more slowly, and its geopotential high is the equator, and everything should be migrating towards the poles. So the average slope is 14 degrees at the coarser resolution or 17 degrees at the 0.8 meter resolution. We don't see a lot of slopes beyond 35 degrees. We do see abrupt changes at plus or minus 25 degrees latitude. I should be more clear here. So kind of this latitudinal band right here, plus or minus 25 degrees latitude. We see high slopes north and south of that and lower slopes in the equator. And the slopes, the flow patterns would be from the high latitudes down to what we're calling the tropics of Bennu here. Another interesting outcome, having the rotation state and the gravity, the mass, allows us to calculate the Roche Lobe. This is defined where surface material would be trapped. So if you're within the Roche Lobe, you're not going to be very easily ejected from the surface of the asteroid. If you are outside it, getting material off of that area would be much easier. And the Roche Lobe, as calculated by Dan Shears, intersects the surface of the asteroid kind of like right here. And then here is the positive polar view to show you what that looks like. That is not necessarily the case. There's no reason why that should be true. The Roche Lobe could be entirely outside of the body. But what we're seeing is that that's creating what we're now calling the fence line, where there's clearly a boundary where the Roche Lobe intersects the surface of the asteroid. And so inside this, in the tropics of Bennu, you would expect material to be migrating and getting trapped down there. So if you're shaking it, if it impacts, if you're spinning it up through a similar phenomena to Yarkovsky called the Yorp effect, or you're inducing a tidal distortion from a planetary close encounter, anything that would cause mass movement downslope, once it gets inside the fence line, it should be pretty much trapped inside there. There are some local highs that we see in there that material might be migrating off of, but that's pretty interesting. We're not sure why that's the case, but that seems to be one of the characteristics of the asteroid. Back to pre-encounter knowledge, so I'm just focusing in on the Ben rock that we saw from the radar. You could see it very clearly in some of the data, and then we did a lot of high-resolution shape modeling to try to constrain its size and shape. And we argued repeatedly to review boards and to selection committees that this asteroid had a very smooth surface, abundant regolith available for sampling. We had 3 lines of evidence for that. First, in addition to the radar ranging, we did radar polarization experiments. So we sent in circularly polarized wavelengths and then looked at how much came back in the opposite polarization. And it looked like it was very smooth at the shortest wavelength, the 3.5 centimeters from the Goldstone transmitter. We expected one 10-meter boulder apparent on the surface. When we looked at the thermal inertia value, which is how quickly the surface heats up and cools off in response to energy input, we had measured a thermal inertia of 310 in these SI units. We thought since that's really low compared to the expected bedrock value of around 2,000, that the grain size should be small compared to the thermal skin depth and therefore on the order of a centimeter. And then this spinning top shape we thought was indicative of spin up of the asteroid and migration of loose material down to the equator to build up that ridge. So we made a lot of claims in the literature about the nature of the asteroid surface. The good news is we got the thermal inertia pretty close. We measured a thermal inertia of 350. We're not seeing a lot of variation of thermal properties with rotation. So here are 2 thermal light curves. This one's from the OVIRS instrument at the 4-micron channel. And then the red curve is using the new shape model, what we would expect the thermal emission to be. So we're doing pretty well. You actually do see some discrepancies here and here. This is interesting. This is right where the big Ben rock, if you watch it come over here, it's right where that enters the shape or leaves the shape. So we think that there's a thermal effect that we're not accounting for with that big boulder on the surface. Same thing with the OTES 14-micron channel. We're doing a really good job predicting the thermal light curve using the shape model and a constant thermal inertia of 350. Probably a variable thermal inertia across the surface between the boulders and the finer patches, and we'll be getting into that more detailed thermal modeling as we progress in the mission. But we got the thermal inertia right, but we definitely didn't get the one boulder 10 meters and larger across the surface. You know, here's the big Ben rock, here's what we call Boulder Town. There's just tons of boulders throughout here. I don't know if it shows up really well here, but there is an elliptical depression here. People have argued, and I think I'll show a slide that claims that this is a crater and that maybe this is a secondary crater. I'm not so sure. It could, because it's centered right on the equator, along with these other circular depressions that are throughout here, although there are other features like that on the north and southern latitudes. These seem to be really prominent. With that low density of 1190 and the match to the CM or CI chondrites, we're looking at a macro porosity in this body on the order of 40%. So you would expect a lot of void spaces in the interior here. So we're also thinking that these might be collapse features of some sort. Maybe if you spun down the asteroid, if it was spinning at a higher rate and material had more centrifugal force at the equator, it would bulge out. And then as the asteroid slowed down, maybe you would induce collapse, and that inducement would be preferred at the equator. But those are all puzzles. This is As I mentioned at the beginning of the talk, up until the past week, my favorite time on the mission was the launch campaign, but there's been nothing like the past couple of weeks at the Drake building with the whole science team gathered together, everybody looking at different features on their monitors, gathering together to discuss harebrained ideas or valid ideas and everything in between as we start to piece together the story of this world. This is the really dark rock over here, so this is just a very high phase angle view, so you're not seeing a lot of albedo variations across here. But overall, I would say, yikes, in the sense that we're going to have to find a spot here that is abundant. TAGSAM can pick up grains on the order of centimeters to a couple centimeters in size. And so we're in for a challenge. We've got a lot of work ahead of us to find a safe sampling site on the surface of the asteroid. The boulders are fascinating in addition to Bennu, which does have one of the things that we were talking a lot about over the past couple days looking at this. It's just perched on the asteroid's surface, and it actually has overhangs. So there's shadows that are cast. We have a whole movie of the different views of it. So this is like a little void underneath it here, and it's just a tiny like mushroom stem where this boulder is contacting the asteroid's surface. And then this face right here is really flat, and it's really reflective. It's up in that 15 to 17% reflective range. The top of the boulder is much, much darker, so it's either got some kind of dust coating or space weathering to change its reflectance properties. We have been leading the witness a lot and calling this the fresh face of Bennu, but that may not be true, and I've warned the team not to jump to conclusions like that. But it sure looks like that this thing, it's been beat up, it's fractured, shattered, and it does look like this might be a fresh exposure. And the bright material might be what's underlying it there. Another rock that we didn't pick up in the radar data is over here. Very prominent, interesting that we didn't see that. And in fact, there's a great study to go back to the radar data now that we have this very detailed shape model and see if any of these features were obvious or apparent now that you know they're there, and therefore improve our radar shape modeling as we move forward. Probably my favorite boulder on the surface is this one. It's about 20 meters in long dimension here. So these are 5 meters or several meter sized clasts. To the meteoriticists in the audience, this looks like a breccia. Very exciting, right? You've got a bright material right here. You've got another one here. You've got a darker material here. You can see the boundaries between these guys. So very exciting. It looks like some sort of regolith breccia, some lithified process of the different clasts around it. And then other areas, this guy over here looks similar, except that it looks like they have completely fallen apart. So same scale, this is about 20 meters across, and you have these different fragments. We've been calling this the funeral pyre, because it kind of looks like a pile of rocks that somebody put up there very intentionally. Organized. So we're thinking that maybe this is a disaggregated breccia, so we're seeing active thermal weathering on the surface as you induce the thermal stresses through the day and night cycles on the surface of the asteroid, causing this kind of disaggregation to take place on site. I mentioned this crater candidate over here. This is something that's being argued about vigorously. I kind of talked about it. It does seem like maybe it's related to this broader elliptical feature centered on the equator here, but when you look at it in this kind of view, you do see evidence of a rim. So maybe it's a double crater, one crater and then another one that landed on top of it, but we're not sure. The ones that I'm getting interested in are these smaller craters. So here we're seeing a whole population on the 10 to 20 meter scale, and the things that make these look really interesting is that this looks like where the fine-grained material might be accumulating. So the bottoms of these smaller craters look like they are maybe where regolith is ponding, the kind of stuff that we could go in and pick up. I'm particularly getting interested in, this is the largest one of those. It's 20 meters. Again, remembering we're at 30 centimeter resolution, so we're going to be sampling one of these pixels on here. But at that scale, this center of the crater looks pretty good. That would be about 10 meters across. Our requirement when we were designing the guidance system for OSIRIS-REx, we had to get into an ellipse that was 50 meters on the long axis. So that would be something like that. That's not going to work. So one of the things I talked to my flight dynamics lead a lot. I sent him this picture, and I said, you got to figure out how to get into something like that. So we're already kind of thinking along those lines. But we got time. There's other regions that look smooth, you know, kind of patches up here or here that might be of interest. And when we do the global mapping during the detailed survey baseball diamond, we'll be getting global 5 centimeter per pixel resolution, so a factor of 6 better than what we're looking at right now. And then we can start to really assess, are these really fine-grained materials when you start to look at things at that scale. And then remembering when we do the low altitude 200-meter flyovers, we'll be getting about 3 millimeter per pixel resolution. So we'll really be able to tell if there's grains that we could grab with TAGSAM before we commit the spacecraft to going in and collecting something. I mentioned the linear features in the north. They really show up in the topographic map. So this is the shape model with a geopotential altitude scale overlaid on it. Again, we're looking at the positive pole. So you do have these ridges that seem to extend down from the pole all the way down to the equator across the entire northern hemisphere. Here's just a little more oblique view. And you do have these lows in between, and you do see material evidence of downslope movement kind of accumulating in these areas and maybe even migrating all the way down to the crater, to the equator. What's going on there, we're not sure. An interesting idea that's been pitched is that maybe these were impact craters and that overall equatorial movement of material is kind of stretching them and elongating them. But again, that's wild speculation at this point. Okay, how did I do? Not bad. So kind of a checklist for how we're doing on the mission. So for the origins, we expected Bennu to be like carbonaceous chondrites. Perfect. Spectral interpretation, we were hoping we would find clay minerals. Got it. For the resource identification, people are interested in water-rich asteroids, so Bennu could be an ore deposit for the asteroid miners. From security, we wanted to know the Arecibo Effect, how well we could use that to determine the mass, density, and the orbit of the asteroid. Really good. And then as the regolith explorer, I'm giving ourselves a yellow check mark right now until, and this was a press conference slide. I actually wanted a red X, but they said that wouldn't play well with the media, so don't do that. I said, okay. And then from mission success criteria, first one, rendezvous with the asteroid. Yes. Number 2 is going to be the challenge, contact the asteroid surface and collect a sample. And number 3 is return that sample to Earth. So we still got some work ahead of us, another 5 years of adventuring to get that material back here so we can get into our great Kuiper analytical facility in the basement here and start picking apart the history of this object at the nanoscale. And we are in good shape there. I didn't mention it earlier, but we did extend the TAGSAM arm. This is the sample collector. SamCam would be right about here, viewing it. So as a checkout, this was through most of the cruise phase. This was attached to the spacecraft with bolts, and we fired those separation bolts and exercised the arm, and we got TAGSAM into the field of view of the SamCam. And I really love this picture. First of all, these are contact pad samplers, so they're basically stainless steel Velcro. We're expecting to pick up grains, so it looks like you might be able to see them on there under this lighting condition. And then even more interesting, this is the arm, this is the wrist, and this is a mesh. So the idea of the TAGSAM is you blow gas down into the regolith and it agitates it up through this throat right here, and it gets caught by this screen. And you can see the shadow of the screen on the interior surface of TAGSAM. And I just can't wait for the image where I see that shadow and there's a grain sitting there that we collected off the surface, and we have confirmation, visual confirmation of successful sample acquisition. But that's probably a year and a half out at best right now. So thank you for your attention. Thank you, Bennu, for inviting me to give the talk, and I think we have time for some questions. Yeah, so that's why we have to do the detailed survey mapping to really assess the science values of these sites. At the end of the day, if that's the only material that's grabbable, then that's what we'll grab. But we'll have the context, going back to Bennu's introduction, right? We will know how this fits into the broader scale nature of the asteroid and the material that we're bringing back. With that 2.7 micron feature, I'm going to be pushing the team to go get that material. That's what we went there to go find. But if it's impossible, right? And we're really looking at a very diverse object here. And I didn't get into the origins of the asteroid and the catastrophic disruption and all of that, but a lot of talk is going on about how many different original parent bodies are here, right? You had the original, probably 100-kilometer or so body in the main belt that was shattered and this is a rubble pile of those fragments. But what about the impactor that hit it? Would any of that have survived and been accumulated here? The wide range of albedo variations is clearly telling us that there's a diversity of material on the surface. Is that space weathering and it's all the same stuff, or is it really truly different mineralogically? The good news is we got a massive mapping campaign ahead of us, and we got time to answer those questions. Tom?
How are you guys going to orbit? Which direction?
So we'll be in the terminator plane. So we'll be kind of orbiting 6 a.m., 6 p.m. And we have to do that because solar radiation pressure is so large a force on the spacecraft. It's comparable to the gravitational acceleration of the asteroid. So we need to keep that constant. So it's not a great orbit for imaging, actually. And that's when we do the detailed surveys, we actually leave orbit and we get into these nice viewing conditions again.
So it's spinning like this?
Yeah, this is the positive pole here, so the right-hand rule. So it's spinning. This would be the morning side here.
So when you're doing
rotating.
spectroscopy, then these point spectra, are they, I don't know how to ask the question, are they sort of smeared out in one direction?
So we're scanning the spectrometers pole to pole, and we let Bennu rotate underneath us. So we take about 90 seconds to go one slew, and then by the time we get back to the equator, Bennu's rotated about half an OVIRS spot size. So if you had a 10, this would be an OVIRS spot right here, 20 meters right here. And then by the time we get back to that spot, the next OVIRS would be there. So there'd be about 50% overlap. Walt?
So going back to your yellow check versus a red X.
Yes.
If you have a 50-meter diameter cross-track accuracy on your site, I look at that right now. Do you think that you have any spot on the surface where you have 50 meters?
No.
Where you're not?
That's why I already told them. We're going to have to figure it out.
Okay.
We're going to have to do better.
Okay.
And we kind of knew that, right? So that was going to be a high, and we actually have contingencies for that. So I think the good news is because it takes so little propulsion fuel to move around this asteroid, what the worst case is, and that was 3 sigma, right? And I'll just say right now we have not had a single maneuver that came in over 1 sigma on the spacecraft. So that's 50 meters, 3 sigma. So at 1 sigma, you're kind of getting into this space right now here. But you can just tighten up the fault protection and abort. So you're coming in and it's like, oh, no, I'm going to land right there. Just fire thrusters and get out of Dodge and then reset and come back and try again. So it's all about that algorithm and the fault protection software that would trigger the abort until you just get it right. Even if it's 1 sigma, 2 out of the 3 times you should be fine, right? So.
Yeah. Okay.
I have a question about sampling and sending it back. So based on what you said, the direction of orbit, how are you going to keep it steady on the location that you want to take the sample?
Yeah, a lot of work's been done on that. So it's moving, the surface velocity is about 10 centimeters per second with that rotation rate and the size of the asteroid. So what we'll do is we'll leave orbit and then we'll fly over towards the site, and then we do 2 maneuvers that drop us down. The first one gets us to 30 meters, and the second one matches the rotational velocity, so we're kind of hovering over that site. We're kind of in like a geocentric orbit, a geostationary orbit. And then we just descend down. We only touch the surface for about 5 seconds to get the sample, and then we get out. That's why we call it a touch and go.
And you said you're going to send it back into 2023?
Yes.
So is it going to be the end of the mission? Or everything going to, are you sending back everything? Or are you still keeping, are you sending only the sample?
So this is the sample return capsule. That's the part that makes it back to the surface of the Earth. This entire sample head will be placed inside that capsule, and this hardware inside this capsule will be what makes it back to the surface of the Earth. The spacecraft, after it drops off the capsule, will stay in orbit around the sun. Yes?
When I look at the surface, it seems like there's a relative paucity of cratering, suggesting that it's quite a young surface. Is that a general feeling from the group?
It's hotly debated right now in terms of if you believe every circular feature on there is a crater and you apply the standard crater ages, I'm hearing estimates of 500 million years for the surface. But I'm not sure if those are craters or not, if they're impact craters specifically. So I expected a young surface. I didn't think we would see any impact craters, or very, very few, and no well-defined craters. I mean, some of these things are clearly impact craters. The concentration of them on the ridge, would, if you just applied that logic, would say the ridge is the oldest structure on the asteroid. And maybe that's true because of all this downslope movement towards there, but area of active debate. And we need the altimetry data to come in. The laser altimeter will really help with this because we'll start to get a lot more views like this at much, much higher resolution to help answer some of those questions. And also the gravity field mapping. That'll take place in that orbit B phase next summer. Was there one here? Here?
Just back to the last picture, maybe. It's beyond just the number of 10-meter boulders that are there. Like you said, 700. They all seem to be very proud above the surface.
Well, like this one here, to me, looks like it's actually being exposed. So not all of them have that. Some of them do, clearly, like Ben here, is sitting right on the surface.
But is the sense that is from maybe an aggregation that is very low energy?
So the leading theory right now,
Or is it from shaking and the heavy ones came up?
I don't think shaking would get you something like that, right? That clearly looks like it landed there. Yeah, so I think we're settling on that. The leading theory right now is that Bennu is a fragment from a catastrophic disruption of a main belt asteroid, on the order of 100 kilometers. That happened 500 million to a billion years ago, and we've actually found some asteroid families that are consistent with that in terms of the albedo and the spectral properties and their Yarkovsky-based age. And that maybe the whole spinning top shape is actually due to the nature of the coalescence of those rubble pile fragments back into it. It had some angular momentum and naturally spun out into this spinning top shape. In fact, Patrick Michel, one of our team members, had a poster about that at the AGU. That's very different than what we thought. We really thought that this shape was due to YORP, which is like Yarkovsky, but instead of changing the orbit, spins up or spins down the rotation rate. And if you spin it up, then you induce angular momentum, and that can drive material to concentrate at the equator. But this is so rounded and smooth, it doesn't look like that. That's really different. Yeah, Allie?
The slopes on those linear features, how do they compare to what you would expect for the angle of repose for if it's material that's moving downwards?
I don't know the answer to that. That's a good question. I don't know. I'd have to go back and look at Holsappel's paper on that just to remind myself. But yes?
Obvious follow-up question is, with the fact that many of the boulders appear to be so proud, due to a loss of volatiles in
Yeah, except that we've got the volatiles, right? We're seeing them in the spectra. It seems like it's a really volatile-rich surface. So maybe, but I wouldn't go there right now because we're pretty excited about the volatile content of the asteroid. So. But I don't know, this is the fun we're having right now. That's why I said it's been a great couple of weeks over at the Drake Building because all these things are being discussed and more. And I didn't tell you all the really crazy stuff that we've heard, just some of the half crazy stuff. All right, thanks again for your attention.